Okay, I'm going to start off this session with just showing you the answers to the practice problems so far. I think we've gone over these before, but just so you can show them, you can pause the video to see them. So this is on 3.1. You can see the answers there. Bottom of the page there, you can see the answers there. $12 is $555,645.52. The second one is $556,385.23. Those are kind of hard to read. On 3.2, there's the top ones. I'm sorry, go all the way to the top. Three point three. I guess that was the end of 3.2 and the beginning of 3.3. $45 is the natural log of x times the square root of x squared plus 4. $47 is the natural log of x on the top, and on the bottom is x plus 2 squared, and that's minus 2 squared. Or on the bottom, if you had x squared minus 4 all squared, that would be fine. 49 is 3. On 3.4, why the one side so much darker than the other side? 51 is x equals negative 5. 53 is 184.444. No matter what I do, it's still dark. There's 55. Get x equals the natural log of 3 and the natural log of negative 2, but that one, natural log of negative 2, does not exist. 57 is x equals a negative 1/2. $59 is x equals 9. It's also negative 1, but that one doesn't work. 61 is 11.55 years. You have to find R first. No, I'm sorry, that's not one you had to find R first. But you did have to, if you let this starts with 1,000, if it doubles, it goes to 2,000. So that gives you your final amount. On B, it starts with 1,000. If it triples, it's going to 3,000. You can still ask questions, and I'll probably try to have another Zoom meeting so we can ask questions about those. That's fine. Now, 3.5. 3.5 is a lot of, it's all application problems. There's a lot of different equations you're going to use. And the equations are at the top. Here's exponential growth. It's actually the same as the PERT equation, except the letters just change. So instead of P here, that's an N naught, that's your initial amount. E, R is your rate of growth. A lot of times you have to find R first on these. T is your time. Here, N is your final amount. So that's growth. Decay is actually the same equation. The only difference is when you find R, it'll be negative. And you can find the half-life, you deal with half-life a lot in radioactive decay. Remember, that's the time it takes for half of the substance to decay. You can do it from the equation, but the shortcut is, if you know the half-life, if you want to find the rate, you take negative natural log of 2 divided by the half-life. If you're the other way, if you know the rate and you want to find the half-life, you just interchange those two. So it's the half-life is a negative natural log of 2 divided by the rate. So exponential growth problems like this first one here, if you start with, this supposed to be a 10 here. If you start with 10,000 bacteria and it doubles every 40 minutes, first you need to find the functions. We're going to take this function we had up here. The N equals N naught E to the RT. We're going to use that same function. First, we're going to plug in to find R. So to find R, we're going to put, it says it doubles every 40 minutes. So if we start with 10,000, in 40 minutes, it's going to be 20,000. So that's our final amount. Then we know the time is 40, so we put that in. So we plug all those in, we're going to find R. So first we divide by 10,000 to get this. Then to get rid of the E, we take the natural log of both sides. That gets us to here. Then all that's left is to divide by 40. So our R is 0.0173. So there's our equation now. We have our initial amount. We plugged our R in. T is what you're usually going to find. Now here it says how many bacteria in 1 hour. Since this was in minutes, we're going to put 60 in for the time. So there's our same equation. We just plugged 60 in here. So you're going to do this part. You're going to do that all in your calculator. Get 28,235. Remember, for E, you hit second ln, and then do this exponent on it, and then multiply by 10,000. On C, it says what time, it says when would mean what time are there 50,000. So go to the same equation we had here. Now our final amount is 50,000. So our equation starts like this. We want to find T, so we're going to divide by 10,000. That'll give us 5. Then to get rid of the E, we take the natural log of both sides. So now we're left with the natural log of 5, and here this all cancels. We have 0.0173t. So all that's left is to divide the natural log of 5 by 0.0173, and our time is 93 minutes. Okay? Now the radioactive decay problem, you tell us the half-life. They tell us the mass. First we need to find the function. Again, first we need to find R. We can use that shortcut over here to find R. To find R, we take negative natural log of 2 divided by the half-life. So that's what we did here. Negative natural log of 2 divided by 140 gives us R. So that makes our equation. There's N equals 300, because that's our initial amount. And there's our R value plugged in there. So there's our equation we're going to use. Find the mass after 1 year. Since this was in days, we need to plug 365 in for time. So we're going to do that on our calculator. That should give us 49.256 milligrams. Don't forget the units, very important. Part C, when does the mass equal 200? So now we take that same equation and we plug 200 in for our final amount for n. So now the equation looks like this. So again, now we're going to solve for t. So we divide by 300. That'll give us 2/3. Then to get rid of the e, we take the natural log of both sides. So now the left side is the natural log of 2/3 here. These two things cancel out. So we're left with that. All that's left to find t is to divide. So we take the natural log of 2/3 and we divide it by whatever r was, and we get 81.9 days. Okay? The next thing, and this is maybe the most complicated formula, is Newton's law of cooling. Newton's law of cooling, the equation looks like this. That's the final temperature. Here that's T, and that's a sub S. That's the temperature of the surroundings. Usually that's room temperature. If you were in the water, that'd be a water temperature. Here, D naught is the initial difference. You take the temperature of the surroundings and subtract the temperature of the object. We need to know just that difference. It's always positive. And then E to the negative KT. K is the constant for whatever the substance is. So there's our formula. Probably the thing that gives most people trouble is the difference. All you do is take the temperature of the surroundings, then subtract the initial temperature of whatever your substance is. So in this problem, we have some coffee that's at 200 degrees Fahrenheit. The room temperature, so that's our initial temperature. Our room temperature is 70, that's the temperature of the surroundings. Our time is 10 minutes, as in 10 minutes the temperature of the coffee drops to 150. So first we need to find K. So the temperature of our surroundings is 70. Our initial difference is 200 minus 70, so it's 130. So if we plug that into our formula, so there's our final temperature, here's our formula we had. We plug in, we know the final temperature is 150. We know the room temperature, the surroundings was 70. Our initial difference is 130, and we want to know, or when they tell us that it's after 10 minutes. So there's our equation. We need to find K, or R. It's the same thing. I think I called it R. It's K for constant or R for rate. Here I think they usually use K for constant. I misspoke before. So now to solve this, we subtract 70 and get 80 over here. Then we divide by 130. So it looks like this. Now we need to get rid of the e, so we take the natural log of both sides. That gives us this. These cancel out. All we're left with negative 10k. Then we take that log and divide it by negative 10. That gives us our k value. So our k value is down here 0.04855. So that's the first thing we need to find is k. So if we plug that in, now our equation looks like this. Now, for A, it says find the temperature after 15 minutes. We're going to take that equation we just did, and we're going to plug 15 in for the time. So that's what we did here. That's the same equation. There's our K value we just found. We're putting 15 in for time. So we're going to work all this out, and we get 132 degrees. So you do this all on your calculator. Now for part B, when is the coffee temperature 100? Now we put 100 in this equation for our final temperature. So 100 goes here. We leave T in because we're going to find T because it says when. So here's our equation. So we're going to solve for T. We subtract 70 and get 30. We divide by 130, get that. Then to get rid of the E, we take the natural log of both sides. That gets rid of this. So now we're left with this. So we're going to take this log and divide it by that K value that got cut off when I copied here. You divide that out, and you get 30.2 minutes. That's Newton's law of cooling. Just as an example, this is what's used if you ever watch a TV show and they want to know when, like if they find a dead body, when that person died, they take a liver temperature. Well, that's what they're doing. They know what the temperature of the liver was for a living person. I assume it's about 99 degrees. They see how much it's dropped. They measure the room temperature, and then they plug it into this equation. That's how they tell them. All right. Then a lot of other things that are used with logs. One is the Richter scale. Richter scale, the magnitude of any earthquake is a log. When they tell you a number, that's a log. So you can't see that very good. So that number is a log. You just take the intensity of the earthquake divided by a standard intensity. You don't really do much with this, except I think it's important to know the difference between, like a lot of earthquakes, you'll hear magnitudes like one is 7.6, one is 6.2, one is 3.2. Well, what's that mean? Those numbers are all pretty close together. You have to remember these are logs, so these are exponents. When it says 6.2, that's 10 to the 6.2. When it says 3.2, that's 10 to the 3.2. So if you compared these two, if you took the 6.2, 10 to the 6.2, divided by 10 to the 3.2, that's 10 cubed. So that's 1,000. That means if the earthquake is 6.2, that's 1,000 times as severe as a 3.2. So if this one knocks down one house, this one knocks down 1,000 houses. I think that's important when you think of earthquakes, that is an exponent. Another thing that logs are used for is decibels. Technically, the first measure of sound was in bells, but that was too big of a unit. It's called decibels because the deci is 1/10, like you know deci from the prefix. That's why the unit for decibels is a little d and a big B. That's 1/10 of a bell. All you do for that is take 10 times the log of the intensity of the sound. And the intensity is this loudness and the pitch, those two things together. Because you know, like if there's a high pitched sound and it's loud, that hurts your ears more than a low pitched sound that's loud. And then I naught is a standard intensity that's just this. That's in watts per square meter, 10 to the negative 12. We won't do much with that. All we do is like find the decibel level. Like here, if I tell you the intensity is 100 watts per square meter, how many decibels is that? Well, you plug that into the formula, 10 times the log of 100 for that intensity divided by our standard 10 to the negative 12. Well, if you divide that out, you get 140, so that's 140 decibels. The last thing on here is pH. You've done pH before. pH is the log. pH is the negative log of the hydrogen ion concentration in a substance. So when they tell you the pH is 6, that's an exponent. That's actually 10 to the negative 6. So if you want to find pH, like here, if I told you the hydrogen ion concentration was 3.16 times 10 to the negative 8, and you want to find the pH, you just plug it into that. So you take a negative log of that value. You do that on your calculator, you get 7.5. So that's a pH of 7.5, which if I remember my chemistry means that is slightly basic, I believe. If you go the opposite direction, if I tell you the pH and I want to know the hydrogen ion concentration, we plug the 2.4 in on the other side, so it looks like this. Now we need to solve for this H, the hydrogen ion concentration. So first we move the negative to the other side. To get rid of the log, we did exponentiate before. We take both sides to a base of 10. So you get that. When you do that on your calculator, you get 3.98 times 10 to the negative 3. That's the hydrogen ion concentration. That was probably kind of fast, but hopefully after part of it, you can pause it, go over that in your notes or on your paper, so hope you can follow what we're doing. We will probably have another Zoom session on Monday to answer questions on this. We'll finish this on Monday. On Tuesday and Wednesday, we'll do work on the review. It's, I think, already posted on the site, but we'll work on the review. And that's it. Thank you.